So this is our so this is our cyclic process. Right, and this was some PV diagram, right? And this was the process, right? So let us say A, B, and C. Okay, so for this part, for this region A to B, right, what would be the work done? This area, right? So this would be the area. Okay, let me choose this one. So this would be the area. Let us, yes, so this would be the area, right? Okay, and for the path BC, the work done would be what? 0, right? Because this is an isochoric process. Okay, so let's say this one is V1 and this one is V2, right? So for AB, this is the work done, right? But for the case of, let's say, CA, for the case of CA, this would be the work done, right? So this would be the work done, right? But this work done would be what? P. This work done would be P. And what is the final volume here for path BC? What is the final volume? Marita. So final volume is V1 and the initial volume was V2, right? But for the path AB in this region, the final volume was V2, right? And the initial was V1. So this part, so this is what? Minus of V2 and V1. So if we add them, this region and this region cancels out. So we are left with this region. So that is why in a cyclic process, we calculate the area which is bounded by this region, the area of the loop. Is that clear, Marita?
Yes, sir.
Yes. So now our next topic was heat engine, right? So this idea was given when? So in 1624, right? And still we are still using this idea in what? In our petrol cars and diesel cars and what turbines and whatnot. So this idea is pretty important, right? So what is a heat engine, right? So heat engine is based on Carnot cycle. So we will talk about that. So this is based on Carnot cycle. So we'll talk about Carnot cycle later. So first, let us talk about heat engine. So what does heat engine do? Right. So let's say this is some source, right, with some high temperature, let's say T1, let's say, right, and this is called the hot reservoir, right, and then some heat is given from this source, right, and this is the gas, right. So this gas then do some work, right, and some heat is released, which goes to this sink, right, which is the cooled reservoir, right? So this is Q2 amount of heat that goes into the sink, right? So the idea of heat engine is that it is some heat is given and some mechanical work is done. So you give some heat and then some work is done. Okay, so this is heat engine. And this is, as I have said, that this is based on Carnot cycle. So what is a Carnot cycle? So Carnot cycle says that we can get maximum efficiency if we follow this cyclic process. So we can get maximum efficiency. So let's say this point is A, and we do this isothermal expansion, right? Isothermal expansion. And then we do the adiabatic expansion. So this is point B. And this is point C. So we do an isothermal compression this time, right? Isothermal compression. And then we do again the adiabatic compression. So this is the idea of Carnot cycle, right? So let me again draw this diagram, and then so this one and this one, and again this one, and so this one and this one. Okay. So this is point A, this is point B, this is point C, and this is point D. Right. So let's say the temperature, the pressure is P1 here, V1 here, and temperature is T1. Now so now the process is isothermal. So let's say here pressure is P2, volume is V2, and temperature will be what? Again T1. Right. And then you do this adiabatic expansion. So you will have P3, V3, and then you have this temperature T2, right? And then at this point, you will have P4 and V4, and then T2, because this process is what? Isothermal, right? So what would be the work done in this process? So can you guys recall what was so the total work done would be what? Would be W, which would be the AB plus BC plus what? CD plus DA, right? So this would be the total work done. So first, let us calculate VAB. So this is isothermal expansion, right? And can you guys recall what was the work done in the isothermal process? What was the work done? Can you guys remember? Do you guys remember what was the work done in the isothermal process? So this was NR, and temperature is T1, right? So NR T1, and then P1 V1 minus P2 V2. Oh, this was ln V2 by V. Yes, ln of V2 by V, right? And in B to C, you have adiabatic expansion. So what was the work done here? P2 minus P1. Yes, so NR and P, and we are going from B to C. So B to C, we have P3, right? P3 V3 minus, okay, so in the form of temperature, what was it? It was,
T2 minus T1.
yes, so it was T2 minus T1 and then upon 1 minus gamma, right? And then for what CD, we have isothermal again. So this would be what NR, and temperature is T2 ln what? So C2D is what V4 and then V3, right? So V4 by V3. Okay, and for D to A, we have adiabatic again. So this would be what NR, and then temperature is from T2 to T1. So final is what T1 and then minus T2 and upon 1 minus gamma. Right, am I correct? So the
Yes, sir.
total work done would be the total of this quantity. Right, so this would be what? So this guy will cancel out, right? So work done would be your NR T1 and then ln of V2 by V1, right? And then plus of NR T2 and then ln of V4 by V3, right? And we can write this as in this form. So NR T1 ln of V2 by V1 minus of NR T1 and then ln of V3 by V4, right? So this is the work done, which is also equals to Q1 minus Q2, right? Because when you see from this point, from the energy conservation, so Q1 goes and W goes out and Q2 goes out. So this comes and W goes out and Q2 goes out. So Q1 is W plus Q2. So W is Q1 minus Q2, right? So this is the work done, and there is a thing called the efficiency of the Carnot engine, right? Efficiency of Carnot engine, or you can say the heat engine. Right. So this is what this is denoted by eta, which is what work done by the gas and the heat supplied. Right. So this is the efficiency, and this is how much? So this is 1 minus Q2, Q1 minus Q2 by Q1. So this will be equal to 1 minus Q2 by Q. Right. So this, but what will be this in the form of temperature? So in the form of T2 and T1, we want to calculate, right? So this would be, so we know that so this would be how much? So let us look at here. So from this equation, so let's say this is 1, right? So W by Q1. So this is how much? So NR T1 ln V2 and then all. Okay, so this was T2, right? So this would be this would be 1 minus, I am cancelling all that that term. So nr T2 by T1, and then ln of V2 by V1, and then ln of V3 by V4, right? So this is the efficiency. Okay, but this can be solved further, right? So you see that this process was adiabatic, right? This V2 to V1 was adiabatic, and V3 to V4 was adiabatic, right? No, not V2 to V3, but V2 to V3 was adiabatic, and V4 to V1 was adiabatic, right? So, so we know that PV gamma is constant, right? Or we can say that NR T by V gamma is constant, right? So this would be NR T V gamma minus 1 is constant. So we can say that T V gamma minus 1 is constant, right? So for this case, so from V3, V2 to V3 for this BC. So for BC, we will have what? So we will have T1, and then V2 gamma minus 1. This would be equal to what? This would be T2 and then V3 gamma minus 1, right? So this would be how much? So this would be T2, and let's take T2 by T1 would be how much? So this comes here. So V2 and yes, V2 gamma minus 1, V2 by V3, right? So T2 by T1 is this in going from B to C. And what about D to A? So from D to A, we will have what? T2 V4 gamma minus 1, right? So T2 V4 gamma minus 1, this would be how much? T1 V1 gamma minus 1. So T2 by T1 would be what? So T2 by T1 would be V1 by V4 gamma minus, right? So these are equal. So your V2 by V3. So by looking into this and this, you can say that your V2 by V3 would be equal to V1 by V4, right? So your V2 by V1 is V3 by V4. Okay, so this I wanted to gain from this diabatic process. So V2 by V1 is so V2 by V1 is what? V3 by V4. So ln V3 by V4. So this cancels. So we have 1 by T2 by T1. So this is the efficiency in the form of temperature. So always remember that Q2 by Q1 is T2 by T1. This you will get, right, in the case of heat engine. Okay, so this is the efficiency, and there is some reverse process which is called the refrigeration. So you have some heat engine, but when you apply the process reversibly or in the opposite direction, so you call this as the refrigerator. right? So in this refrigerator, you had some, so this was some source, and this was the diagram, right? So this was the sink, and this was the source, right? So in the heat engine, we supplied some heat, and then the work was done. But for the case of refrigerator, we take some heat from this sink, and then we also, the work is done in this system, right? And then it provides some heat. Okay, so this is called the refrigerator. So from the energy conservation, you can see that your Q1 would be what? W plus Q2. So W plus Q2, right? So now in the case of refrigerator, you have a coefficient of performance. Performance. So coefficient of performance is defined like this. Okay, whatever whatever the heat you take from this sink, and whatever the work is done on the system, then this is called the coefficient of performance, right? So you know that your W is how much? So your W is Q1 minus Q2, right? So this would be Q2 by Q1 minus Q2, right? So, okay, so you know that this would be again, so this is called beta. Okay, beta is Q2 by Q1 minus Q2. So we can write it as T2 by T1 minus T2, right? So this would be how much if we divided this by T1. So this would be T2 by T1, and this would be 1 minus T2 by T1. Okay, so you know that this is what? This is what? Guys, this is, we have derived this earlier. This is, this is the efficiency, right? And what is T2 by T1? So we have to write this T2 by T1 in the form of this efficiency. So efficiency is 1 minus T2 by T1. So T2 by T1 would be what? 1 minus efficiency, eta. So this is 1 minus eta. Okay. So this is the coefficient of performance in the form of this efficiency, right? So always, so for the case of this heat engine and this refrigerator, always remember this diagram. This diagram, if you know, then all your other work is simple. Right. So for the case of this heat engine, this would be Q1, this would be Q2, and the work would be done here, right, by the gas. Okay, so this is T1 temperature, this is T2 temperature, and your T1 is greater than T2. For the case of what, refrigerator, you take some heat from this, and then you do this work. Okay, so this is T1 and this is T2. Okay, and what are the basic formulas that we have derived here? So your efficiency is what? W by Q1 for the case of this heat engine, and this we derived as Q2 by Q1, which was 1 minus T2 by T1, right? And This beta was what? Q2 by W. So that was Q2 by Q1 minus Q2. So that this was 1 minus eta and then eta. Okay, this much we all need to know about this heat engine and refrigerator. Okay, so this concept part is done, and now let us do some question based on this. So that is why this chapter is very important, because they ask you some direct questions based on this. So they can't what make some changes in the idea, or they can't use idea from other place and so on. So they can only ask some direct questions from this because this is some fundamental concept. Okay. So the first this 33 number question, very difficult, very difficult question. Okay. One can have some shivering in his body, in his body, in her body, his or her, because this question is very tough. Okay. The efficiency of a Carnot engine depends upon the temperature of the sink, the temperature of the source and sink, and the volume of cylinder of the engine. Volume of cylinder, why does it come? The temperature of the source on. Yes, so who has done the most difficult question? Marita, yes. Samara, right. Yes, so you guys have done a very difficult. Yes, so we all know what is the efficiency, 1 minus T2 by T1. And this is temperature of source and this is temperature of sink, right? So it is dependent on both source and sink. Right, guys? So yes, Samira and Marita, you both are correct. Okay. Yes, so this one is correct. Okay, now this second question. The efficiency of an ideal heat engine working between the freezing point and the boiling point of water is. Okay, before I move further, I forgot to mention a very crucial point. This was a very crucial point that I forgot to tell you, that this temperature is in Kelvin. Okay. So this idea holds for this Kelvin temperature, right? So whatever the temperature is given, you have to change that into Kelvin, right? So this is a very crucial point. Okay. Always keep this in mind. Yes. So the efficiency of an ideal heat engine working between the freezing point and boiling point of water. So your T1, you all know that T1 is greater than T2, right? So T1 is the boiling point, which is what? 100 degrees C, which is what? 100 plus 273, which is 373 Kelvin. Right, and T2 is how much? 0 degrees C, right? So this would be 273 Kelvin. Okay. Yes. See, yes. Let us check. 26.8. Okay. So what would be the efficiency here? So this would be minus T2 by T1. Okay. So this would be how much? 1 minus. Perfect. Okay. So two guys got. Yes. So this is how much? 273 and by 373. So this is how much? Let me use my calculator. Okay. You guys divide, but I can use the calculator. Yes, so 273 divided by 373. So this is how much? 0.73 So 1 minus 0.73, right? So this would be how much? 732. Okay, so this would be how much? 8, and then what? 936, and then this would be how much? So this would be 9 minus 2, right? So 0 point. So this is in the, this is not in the percentage, right? But the answer is in the percentage. So we will multiply this by 100, right? So 26.8. Yes. So Marita and Arpit got the right. Okay. Any doubt, guys? Any question? Any question, guys?
No, sir.
Okay. Now let us do this problem. So a Carnot engine having an efficiency of 1 by 10 as heat engine. And then this is used as a refrigerator, right? So if the work done on the system is 10 joule, the amount of energy absorbed from the reservoir at lower temperature, right? So the amount of energy absorbed. So let us recall the diagram of that refrigerator, right? So this was the diagram of that refrigerator, right? So the work done is given 10 joule, right? And we have to calculate Q2, right? And what do we know? We know that performance is what? Coefficient of performance is what? This is Q2 by W, we know, right? Right, guys? So Q2 we have to calculate, right? And W is given 10 joule, right? And beta is not given, but eta is given, right? So eta is 1 by 10. So we can calculate beta, right? So beta would be 1 minus eta by eta. So this is how much? 1 minus 1 by 10 by 1 by 10. So this would be 9 by 10 and then 1 by 10. So this 10 cancels, so we have 9. Okay, so we now know beta. So beta is 9 and then Q2 by 10. So Q2 would be how much? 90. Right, guys? So this would be the answer. Okay. Uh, one there is also one another method that we can calculate this question. We can, there is an alternative method. So we can also use this idea of heat engine, right? So for the case of heat engine, we had this Q1, and then this goes into this so Q2, and then this work done. So work done is given 10 here. So Q1 Q1 was how much? W plus W plus what? But before I do that, yes, so Q1 was what? W plus Q2, right? And we know Q1 was how much? W is how much? 10 joule, and Q2, right? We are looking at this heat engine first. Okay. So Q2 we can calculate from this heat engine, right? So from this heat engine, we have this minus Q2 by Q1, or W by Q2. Okay, so this is how much? So 1 by 10, and then W is 10 and Q2. So Q2 is 100, right? So this is 10 plus 100, right? So this is how much? 110. Okay. Now did I? So this is Q1, right? So this is Q1, right? So this would be 1 by 10 and then W by Q1. So Q1 is what, 100? Okay. So this, so we can now calculate this Q2, which would be what? Which would be 90. Okay. So Q2 would be 90. Okay, but now let us look into the refrigerator part. So for the refrigerator case, we have what? So this Q2 is taken and this work is taken and this is Q1, right? So we have to calculate the amount of energy absorbed from the reservoir. So we have to calculate Q2, right? Okay, so we have to calculate Q2 and Q2 will be what? Q2 would be, this is W, so Q1 is W plus Q2, right? Q1 is 100 and W is 10 and this is Q2, right? So Q2 would be how much? 90. Okay, so you can either use this descriptive method or you can use this direct beta and eta relation. Okay, any doubt, guys? Any doubt, guys?
No, sir.
Okay. Now let us come to this question. Okay. Our refrigerator works between 4 degrees C to 30 degrees C. So what is T1 and T2 here? T1 is how much? 30 degrees, right? And T2 is 4 degrees. So 30 meaning 30 plus 273, right? So this would be how much? So this would be 303 Kelvin. Okay, and 4 degrees C, which means 4 plus 273, which would be 277 Kelvin. Right, guys? So it is required to remove 600 calories of heat every second. So this heat is removed from this sink, right? Okay. So Q2 is given, right? 600 calories, and you guys know what is calorie in joules. So this is given here, right? So 600 into 4.2. Okay, so this would be how much? 12 and right. So this is this much joule, right? So we know Q2, we know T1, T2, right? Now, what they are asking, it is required to of heat every second. The power required is, right? So for power, we need work, right? So power is work upon time. Okay, so we need work. So how can we calculate the work done here? Okay, so we know that this W by Q2 or Q2 by W, right? Q2 by W is how much? This is T2 by T1 minus T2. Right, guys? Am I correct? Right, guys? So we know Q2, right? So we can calculate and let's reverse this. So this would be how much? So W by Q2 would be T1 minus T2 by T2. So this would be W would be T1 by T2 minus 1, and then this Q2, right? So this would be how much? T1 is how much? 303. And this is 277. Okay, minus 1 into 2520 joules, right? So this would be 303 minus 277 by 277 into 2520 joules, right? So this would be how much? So 6, and this is 2, and what? Yes. So 26 277 into 2520. So let me let me again use the calculator. So this would be how much? 26 into 2520 divided by 277. So this is 236.53. Okay. So are you guys allowed to use a calculator in your exam?
No, sir.
Oh, so that is problem. Okay. So you guys divide and then calculate, right? Okay, so this is 236 joules, right? So the power would be, they are asking about this work done in each second, for every second, right? So time is 1 second. So W by 1, so this would be 236.53 joules per second, right? Okay, so this is the answer. And what about this 37th number question? Okay. So any idea how should we do this question? Guys, any help? Any suggestion? Anything? The temperature inside a refrigerator, so both the temperatures are given and they are in degrees Celsius, right? The amount of heat delivered to the room for each joule of electrical energy. So work done is given, which is 1, right? Work done is 1 joule given, okay? And the amount of heat delivered to the room. So they are asking about Q1, okay? The amount of heat delivered to the room. So Q1 they want us to calculate, okay? Because this is this system, right? So this takes from this refrigerator inside this temperature, and this is the temperature that goes to this room, to the environment, Q1, right? So they want us to calculate Q1, right? So what do we know, guys? What do we know? First, let us change this T2 into what? Degree Kelvin. Okay, so T2 would be what? T2 plus 273 Kelvin, right? And T1 would be, let's say, in Kelvin. Okay, okay, okay. So this would be T1 plus 273 Kelvin. Okay, so we know that what is Q2 by W, and W is 1 joule here. Okay, so we know that Q2 by W is T2 by 1 T1 minus T2. Okay, right, guys? We know that Q2 by W, Q2 by W is this, right? Right, guys, am I correct?
Yes, sir.
Okay. Yes, so Q2 would be how much? T2 is T2 plus 273 by T1 plus 273 minus T2 minus 273. Right, so this cancels. So we have T2 plus 273 by T1 minus T2. Okay, so this is Q2. But they want us to calculate Q1 here, right? So because Q1 is the heat that goes out to the room, that is delivered to the room. Okay, so now we can apply the total energy criteria, total energy conservation. So again, I am saying that always remember this diagram. So if you remember this diagram, so the questions become simpler, right? Okay, so your Q1 is how much? W plus Q2, right? So W is 1 here. So this is 1 and plus Q2 is how much? T2 plus 273 divided by T1 minus T2, right? So this would be how much? So this goes here. So T1 minus T2 and plus T2 plus 273 divided by T1 minus T2. So this guy cancels. So we have Q1 equals to T1 plus 273 divided by T1 minus T2. Okay. So yes. So we have to always check what they are asking. So he delivered to the room, right? So we calculated this Q2, which was taken from this refrigerator system heat, right? So this was T2 plus 270. So this option was also given, and this option was also given. So we have to keep in mind what they are asking, right? So the answer is what? This. Okay, any doubt in this question, guys?
No, sir.
Why do we take W as equal to 1 in this question?
Because you see the amount of heat delivered to the each joule, right? For each joule of electrical energy, right? So they have given work done as. Now 38, this type of question we did, right? Oh, so guys, please do the honors, right? Who is volunteering? Because guys, this is our last class, so help me a little this time. In your earlier classes, you were helping, but in the middle, you got what? Your energy exponentially decreased, and then it got to a saturation point. At whatever I am asking, then saturation. Okay, yes. So, guys, please do this question. Okay, who is doing this question? This was similar to the question that we did earlier. So the amount of energy absorbed from the reservoir at low temperature, right? So amount of energy absorbed from the reservoir. So they are asking to calculate this heat, this energy they are asking, right? So we have done this question. You just need to calculate this. So this was what? Q2 by W, right? So please calculate and tell me the answer. Hmm. Yes, C. Okay, Samara has also got C. Now, let us check. There are what, 5 people? So 2 have answered. Let us wait for all the 3 guys, right? This time I won't spare you guys. Because what, we have very few questions, right? And we have half an hour. So, yes, who else? Yes, Anna. Now Anna has spoken. Yes, and who is left? Guys, because if I would be solving all the question, then that would be good for me only, right? Then I would only be practicing, right? But I'm not taking the exams, right? You guys are taking. So it would be good if you guys try. Okay. Because if I do all the problems, then my problem solving will enhance, right? But that is not the goal. Who is left? Iram and let me check. Arpit. Arpit, what about you? Arpit sir, what has happened to you? This is the same question, exactly the same. The numbers are also the same. Okay. Yes, yes, so this was the same question as we did before, right? Let me up this part. So we calculate beta first, right? So beta is how much? 1 minus eta by eta, 1 minus 1 by 10, 1 by 10, then 9 by 10 by 1 by 10, then 9. Right, and then from beta, you calculate what? Q2. So 9 by Q2 by W, which is 10. So this is 90. Okay, guys. Okay, now let us come to this question. Okay, the coefficient of performance of a refrigerator is 5. So beta is given. Right, guys? So beta is given, which is 5. Okay, and if the temperature inside a freezer is minus 20 degrees C. Okay, so T2 is given. Minus 20 degrees C, which means 273 minus 20, which is how much? This is 3, and this is what? 5, so 253, right? 253 Kelvin. Always remember that we have to change this degree Celsius to Kelvin, always. Right. So the temperature of the surrounding to which it rejects heat. So we have to calculate T1, right? So again, the usual formula. That is why I am saying, I keep saying, guys, that they ask you direct questions based on this thermodynamics, right? So these are quite easy, and you can score marks if they ask you such kind of questions. So yes, beta is given, right? And this is how much Q2 by W, and this is how much T2 by T1 minus T2, right? So 5, and T1 we want to calculate. So this is 253 by how much? T1 we want to calculate minus 253, right? So this would be how much? 5 T1, and then minus of 5 into 253, which is 253. So this would be how much? 5 T1 is 253, 1 plus 5, so this is 6. So T1 would be what? 253, 6 by 5. So this is 1.2. So this is how much? Right. So 303.6 Kelvin. And this would be how much? So the options are in degree Celsius, right? So we have to change this again in degree Celsius. So 3.6 minus 273. So which would be what? 6, and this is 0, and this is how much? So this is this. So this is 3, right? So which are the close? So which are the closest? Which one is the closest? This one, right? So this is the answer. Okay, guys. Any question in this? Any doubt in this question?
No, sir.
All right. Okay, let us do this question. So an engine has an efficiency of 1 by 6. So eta is given, right? So eta is given 1 by 6, right? When the temperature of sink is reduced by 62 degrees Celsius, right? So whatever the temperature of sink was, this was T2, right? So eta is 1 minus T2 by T1. So this is 1 by 6, and 1 minus T2 by T1. So this is how much? So this goes here. So T2 by T1 is how much? So this is yes, T2, and then 1 minus 1 by 6. So this is 5 by 6. So what is given? T2 is given, right? T2 by T1 is 5 by 6. So T2 is given, and we want to calculate T1. So T1 would be what? 6 by 5 T2, right? So this we know. And what is the second condition? When the temperature of the sink is reduced by 62 degrees Celsius, which means by how much? So 273 plus 62, this is how much? 5, and this is 335, right? So this is reduced by its efficiency is doubled, right? So this is double of this is how much? 1 by 6 into 2, so 1 by 3. 1 by 3 is equal to 1 minus T2 by T1, right? And 1 by 3 is how much? 1 minus, let's say, T2 prime, T1. So T2 prime and yes. So T2 is reduced by how much? So let me calculate T2 by T1. This is 1 minus 1 by 3, which is 2 by 3, right? So 2 by 3, and then we know that T2 is reduced by how much? 373. So T2 minus 373, right? Which is T1, and then we have what? And then we have T2 by 3, right? So we know that we can write T2 as 5 by 6 of T1, right? So 5 by 6 of T1 minus 373 by T1, which is equals to 2 by 3, right? So this would be how much? So this would be 5 by 6 minus 373 by T1, and then 2 by 3. Right, so this would be minus 373 by T1, and then 2 by 3 minus 5 by 6. So this is how much? This is 6, and this is 4 minus 5, and this is 373 by T1. So this is minus 373 by T1. This is minus 1 by 6. So T1 is how much? 373 into 6. Okay, so 6 threes are 18, and this is how much? So okay, so 6 threes are 18, and 6 sevens are 42, and then 43, and then right. So this Kelvin, and then the answer is in degree C, right? Okay, so we are getting a huge number. Okay, so you guys check what where I made a mistake, right? You guys check and then you guys correct that. Okay. So you guys please check that. Where did I make a mistake? Okay. Now let us come to, okay, so we have 3 questions and 15 minutes. Okay, so let us do this question. You guys please check where did I made a mistake. Okay, so please check. So this next question is a Carnot engine whose sink is at 300 Kelvin has an efficiency of 40%. So eta is how much? Eta is, you guys please check where did I made a mistake. Okay, so a Carnot engine whose sink is at sink, meaning T2 is given, right? 300 Kelvin, and has an efficiency of 40%. So eta is given 0.4, right? So by how much should the temperature of source be increased so as to increase its efficiency by 50%? So 50% meaning that whatever this is, so 50% of this would be what? 0.2. So new eta is what? 0.6, right? So new eta is this, and by how much should we? By how much should the temperature of source be increased so as to increase its efficiency by 50% of original? So n prime would be what? 1 minus T2 prime by T1 prime, right? So should the temperature of source be increased? So this source temperature, right? So T1 should be increased, right? So from here we can calculate this T1 temperature, right? So T2 is given, and 0.4 and 1 minus T2 by T1, right? So this would be how much? So this is minus 0.6 T2 by T1 minus, right? So this is T1 is 0.6 into T1. So 0.6 and what was given? T2 was given. Okay, so T2 into T1. So T1 is 300 divided by 0.6. So this is how much? So 50. So 500 Kelvin. Right. And by how much should the temperature of source be increased so as to increase its efficiency by 50% of its original efficiency, right? So T1 was 500 Kelvin, but they want us to, so this new, now we should calculate what would be the temperature for this new efficiency. So this is 0.6 and this is how much? 1 minus 3 divided by T1. Right, so this would be how much? 0.4, okay, minus 300 by T1. So this would be how much? 300 divided by 0.4. Right, so this would be how much? So 2, 5, and then so this is okay. So this is how much? 750, right? So what is the difference here? 250, right? So this is the answer, right, guys? Am I correct? Any? Yes. Okay, Arpit. Now you have started solving. Yes, 250 Kelvin. Okay. Yes. So now let us do this problem. So any doubt up to this point? Any doubt, guys? Any question up to this point? Guys, any question up to this point?
No, sir.
Yes, sir.
Okay. Now, so let us do this question. And then I will give you guys this question. Okay. And did you guys made some short notes, whatever we were learning? So you guys wrote down all the formulas and all, so that you can keep track of whatever you have learned so far. Whenever you looked at and something like 4 or 6 pages of some formulas that you need to recall at the end of the time. So did you guys made those? Hmm. A very precise, concise note that I'm asking. I asked Anna, and she said that she has made one. So did you guys also made one? Hmm? Okay, I assume that you guys all have made one. Yes, so an ideal gas heat engine operates in Carnot cycle between 227 degrees C and 127 degrees C. It absorbs 6 into 10 to the power 4 calorie of heat at higher temperature. Amount of heat converted to work is. Right, so they want us to calculate the work done. Okay, and the answer is in calories, so we don't need to change this in joules. Okay, so first T1 is how much? 227 degrees C, and we have to change this in what? Kelvin. So 227 plus 273. Right, so this would be how much? So 0, 0, and 500. Okay, and T2 is how much? 127. So the difference is 100, so that would be 400, right? Right, so this is, yes, 6 by 5, yes, 6 by 5 into 10 to the power, yes. 6 by 5 is how much? 1.2, right? So 1.2 into 10 to the power. Okay, let us check. So, and it absorbs 6 into 10 to the power 4 calorie of heat at higher temperature. So Q1 is given, right? 6 into 10 to the power 4 calorie, and uh, amount of heat converted to work. So what do we know? We know that eta is how much? T2, yes?
Yes,
Yes,
it's but I did the other one.
you did the other one, meaning?
No, sir, I said it's correct, sir. I calculated first the E, then I put in the formula E equals to W from.
Yes, 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 yes. 2.4 into 10 to the power 24, right? So this is how much? Let us check. So Arpit answer is C, and Marita answer is A. So let us check which one is correct, right? So this would be how much? T1 minus T2 by T1, right? So this is how much? So 500 minus 400 divided by 500, right? So this would be how much? 100 by 500. So this is 1 by 5. Okay, and what is eta with respect to heat? So this is W by Q1, right? Right. So W is how much? W is Q1 by 5. So Q1 is how much? Q1 is 6 into 10 to the power 4 and divided by how much? 5. So Arpit got this. Okay, so 1.2 into 10 to the power. Mahita, you check your answer, right? Where did
Yes.
you? Okay, so this one is right. And now let us come to this last question and to the end of our journey, right? 2 months or 2.5 months, whatever. Yes, so let us, I will give you guys this question. So please calculate and what I would share, I would say that all the best guys for your exams, all the very best. Whatever, best of luck, best of best of time, best of, so whatever, all the best you need, that is all the best. Okay. So please guys do this question and tell me the answer. Then that would be all from my side. So who is solving this question?
Yes.
So B, 100 plus 23 by 373. Okay. And who else got B? So the efficiency of Carnot engine, 1 minus T2 by T. Right. So T1 is what, 100? So 373. And T2 is how much? Minus 23 plus 273. So this is 0, this is 5, and this is right. So this would be how much? So this would be T1 minus T2 by T1. Right. So T1 is how much? 373 minus 250 by T1. So this is how much? 373 minus 250 is what? 3 and then 2 and then yes, T1 is yes. Yes, Anna also got Arpit, Anna, right. Right, guys. So this is yes, this is good. Yes, so 123, and why did they write like this? 123 by 370, is that not good for these people? Like, yes, so 100 plus 373. Right, so this is the efficiency. Okay, guys, so all the best, guys, for your exams, right? And you guys will do good, inshallah. Okay, guys, any question up to this point?
No, sir.